Hello, Duel. I will start sharing the screen, and if you can remember, yeah, we started in coffee, and we were talking about a little bit of chaos theory and a bit beyond. I hope you are okay with not with everything, but with everything we have, not everything, but are you now getting a feeling? Are you kind of, yeah? Hello. Yeah, are you okay with everything we discussed that day? Right. So you don't need to remember. The good news is you don't need to remember everything we have discussed because it's a very vast concept, right? Something yeah, it's very difficult to comprehend actually. Even though yeah, at the beginning because it's a very brand new concept. So as long as you can understand why entropy is needed, do you understand why it's needed? Yeah, the importance of Now we talked about endothermic and exothermic reactions. Some reactions are there endothermic, but we had to explain why these reactions happening. In order to learn what that hidden factor is, we had to come up with this concept. Yeah, can you hear me? Yeah. So in order to come up with that concept, because we had the endothermic and exothermic reactions, endothermic reactions are kind of non-spontaneous, but there are spontaneous reactions of endothermic also. So we were struggling with explaining the endothermic reactions in terms of enthalpy. Therefore, they had to come up with another theory, and in that theory, they asked a thing called entropy, right? Okay. Is that clear? Why entropy is needed to explain some reactions? Very good, right? Not only endothermic, even exothermic, but mainly endothermic reaction. So, did you understand something on like only at the surface level? Uh, the universe is always preferring what? Order or disorder? What does universe prefer? Universe prefers disorder. When the disorder is greater, more disorder. So therefore, there's more entropy, right? Right. Yeah. That is why solids prefer to become a gas. Why? When the particles are there are when there are more gaps, right? Particles can arranged in many ways, right? Now, if I ask you what is entropy, how do you define it in your words? Very good. That's all you need to know. And one more thing I will tell you: energy, right? Energy in less physics you are learning this. Even energies is particles, right? Quantum particles, is it? So therefore we learn number of arrangements particles can have. So even you can convert that into energy. You can tell number of different ways energy can have, right? So even in terms of energy also, because energy is also there as particles, right? So actually the real meaning is, if I tell you the most correct, most appropriate definition for entropy is number of different ways energy can disperse, right? As that. So that's all you need, nothing else. So what you have understood is a very deep concept, right? So you were able to understand because you got a slight idea about the background story. We talked about, if I tell you why universe is expanding, and the universe is expanding, right? There are many more gaps, right? So therefore there's more disorder. That is why universe is expanding. I will ask you one thing. This thing I haven't discussed. When a system is more disordered, what can you tell about randomness? I hope you know what it means, the English term for randomness. When very good. So sometimes even some teachers they think, even some students they think entropy is randomness. No, entropy and randomness are two different things. But in a system, if the entropy is larger or greater, randomness also becoming greater or larger. Otherwise, randomness and disorder, randomness and entropy are two different things. But in a system where entropy is greater, randomness is also greater, right? You get the point? Okay. Right. Then let's move on to some questions, right? If you can understand that, you are okay. Right? Give me a second. Right. That's all you need to understand. Yeah, and the physical chemistry part too. We were talking about endophthalmic. Uh, right. So we were right. So we were talking about chaos in the universe under entropy. So we know why do we call it chaos? Chaos means more disordered. The universe is chaotic, right? You understand that thing, right? Why do you call it chaos in the universe? Yes, right. Now I will give you a question now. With your knowledge in entropy we have discussed so far in your syllabus, AQA, can you explain if someone tells you at a certain temperature and pressure, this reaction is happening spontaneously. How do you explain in few words? If someone tells you at a particular temperature and pressure, this reaction is happening spontaneously. Can you explain why? And why it has increased? Very good. First point. When in from a solid to gas. No, 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 no. When you are talking about entropy, do not talk about intermolecular forces, right? Intermolecular force. Why? There are particles are further apart. There are more gaps. In a solid, particles have more fixed arrangements. So therefore, it is more ordered. Liquid is disordered. Why? Solid is. Let's write here. Now you should write in your own words. Huh? This is what solid particles are fixed, therefore more ordered. Here it's a liquid, so therefore particles are loosely or arranged. Loosely arranged. So therefore relatively disordered. Disordered. So therefore order means less random movement. Less random, more random. So therefore less entropy to high entropy. Right. And the chaos theory tells you in the universe or in a system, more entropy is preferred. So I can tell you, universe prefers. You should tell that also, right? Universe prefers prefers increase of entropy, right? Let's the best word is entropy. Increase of entropy in a system or in the universe, right? Because we have to talk about the entropy in the universe, right? It's a universal concept, not just about our Earth. Now put the subheading as feasible or spontaneous reaction. Spin heads. Feasible or spontaneous. These are related to each other, right? Now, feasible or spontaneous means, now remember, suppose feasibility or spontaneous comes, right? Technically, it means thermodynamically how we explain this. If a reaction is, if someone tells you it is feasible or spontaneous, right? It means, in other words, it's called energetically favorable. Right? A reaction becomes feasible or spontaneous when a reaction is energetically favorable, right? Energetically favorable. Energy means heat. So under this energetically favorableness, it includes enthalpy. Yes, it's the same thing. Feasibility, spontaneous. They will tell if a reaction is energetically favorable, they may tell you a reaction is feasible or spontaneous. Same thing, right? A reaction becomes feasible or spontaneous when the reaction is energetically favorable. It's the same thing. So under energy, right? We are considering these things. Enthalpy is the topic under energy, and entropy is also these things. To know whether the reaction is energetically favorable, we should know about enthalpy, entropy, and later we are learning something about what? Gibbs free energy, and also temperature. Temperature, right? So all these things are there, right? Right? So we can tell, right? So we can tell whether a reaction is energetically favorable by applying the second law of thermodynamics, right? Second law of thermodynamics. Dynamics, right? As per second law of thermodynamics, we can tell whether reaction is feasible or not by looking at its energetically favorableness, right? Based on which law we are telling about it by using the second law of thermodynamics. So, in brief, what does it tell you? Second law of thermodynamics tell you in brief, if you can talk about universe, our universe is expanding. No? So when the universe is expanding, why universe is expanding? When the universe expands, entropy increases, right? That is why. When the universe expands only, entropy increases. So our universe is spontaneously expanding, right? So second law of thermodynamics tells you entropy of the universe is increasing. Of the universe is increasing. This is what it tells you. It tells you the entropy of the universe is increasing. Now, it is the same reason, and this is not chemistry, right? So, you ever wondered, I told you, why, uh, okay, when you drop a cup on the floor, why it breaks into many pieces? Why can't, is it the gravity? I don't think so. Yeah, gravity is there. So, why it breaks into pieces? Now, if there's gravity, why the pieces are, we cannot collect the pieces, and why does it happen in reverse? If you, why it is not a reversible reaction? The cup breaks into pieces. Why a broken cup cannot be made into cup again? Why can't you do it in reverse? Why it is always a one-way journey? If I ask you like that, yeah, it was broken. Why can't you reverse that reaction? You can't never fix a broken cup. It never works in reverse, right? Why? If we can break it, we should be able to make it in reverse. Why? But still, no, you can't get the original piece, right? Even if you have glue, you can't. Why is that? You can only explain that with what? Entropy. What do you think? When the cup is broken, what happens? Entropy increases, right? That's the reason. Here's the cup, and you drop it, and you have the pieces. Less entropy, less entropy, high entropy. Less entropy to high entropy. Only to less entropy to high entropy, not the other way around. Less to high, not the other way around. It can explain you many things. I'll move on to that. Right? The most important thing. Right? Yeah. Is was I will come to that later. Like I'm going to, yeah. It's the same reason why in hot objects always what means hot objects. So I told you energy is particles, right? From a hot object, why heat is moving out, why it is spreading inside the hot object. the energy particles are near each other, close to each other. One, but when it is moving out to the surroundings, these energy particles or heat particles are further apart. So therefore, in the surroundings, at the surrounding, the heat has high entropy. Inside the club, it has less entropy. So same reason why heat is always going out of a hot object to the surrounding, not the other way around. Right? Heat always moves out of a hot. No, no, low entropy, high entropy. Other way around, right? In the cup, no, it is hot. When it is hot, right, it has energy. So inside the cup, it has heat energy. That heat energy is going to the environment. So when it is in the cup, its heat is near each other in order. Heat particles are at one place, centered in one place. But when it is dispersed to the surroundings, heat particles are spreading out just like a cup. So when it is in the cup, less entropy. When it is in the surroundings, high entropy. Heat spreads. Understood? Very good. Entropy always moves from left to right. That's the second law of thermodynamics. If you ask me why entropy always increase, that is second law of thermodynamics. Right? Heat always spreads out of the hot object to the surrounding. I'll come on to that, right? The most interesting one. I'll ask you that question. Let's see whether you can answer it. When there's an earthquake, what happens to buildings? They breaks and come into pieces. So entropy increases, right? Why doesn't happen in reverse? The buildings are not getting fixed themselves. Why? Very good, right? Very good. Buildings gets destroyed by earthquakes. See how interesting these topics are. You can explain many things, right? Buildings gets by earthquake. The most important thing, right? Let's see whether you can answer it. Why can't you bring a dead person back into life? When a person is dead, he is dead. Why? Yeah, when you die, what happens to your entropy? It increases. When you die, what happens to what happens to your body? Your body is getting into, yeah, your body is getting decomposed, right? If you know, right, if you bury a dead person in soil, what happens? Your body is getting decomposed, separated into little pieces, right? Okay, now when you are living, what are you actually doing? Why do you eat? Why do you call living is a struggle? Why? This is our body. Our body is ordered, well structured. But our body is trying to get into disorder. Our body is functioning orderly. Everything is happening in order. But our body naturally prefers to, we are getting sick. We are getting wounds. Right? Our body is trying to get into disorder. So we have to work against it, right? For that we have to put some. That is why we are eating and we are struggling. We are doing a job. We are learning. We are trying to keep it up while our body is trying to break it apart. So until we die, we are in a struggle. But what happens when we are getting old? Why? We are trying to reverse it. We are struggling means we are trying to reverse it. We are trying to decrease it in. We are trying. Yeah, we are trying to make the entropy lower, but we can't do it. That is why we are getting old, right? That is why we are getting old. Why? When we are getting old, little by little, our body structures are what is happening to our skin. It is falling apart, right? Our body is falling apart. Our bones are getting cracked. Can we stop aging? No, we can't. We can slow the process. We can slow entropy from going up. We can slow it. That is why we are eating, we are exercising, we are maintaining our body, but we can't stop it from happening. Even slowly it is happening. That is why we are aging. And finally, what happens? We are losing the battle, completely getting decomposed. That is why we can't bring a dead person alive. Right? That is why we can't stop aging. We will never be able to stop aging. Our cells are dying. Our cells are aging. Our DNA is aging. From the day we were born, and until we die, and even after die, still we are, because we are part of the universe. We are decomposed. We are part of the universe. If the universe is designed in that way, we can't stop it. Our universe is designed, our whole universe entropy is increasing. Our whole universe is falling apart. So we are part of the universe. So how can we stop it? We can't. That is what we call nature. Some people may call it even God. Universe, entropy. Entropy is the driving force of everything. That is the driving force. We can't reverse it, no matter what. Because we are also part of it. We can't reverse the universal entropy from going from increasing to decreasing. We can't. It is increasing, no matter what. We are also part of the universe. Our bodies are falling apart. Since we are a creation of universe, we are part of the universe. If the universal entropy is increasing, there's no other way to stop it from happening. We are also what? From the day we were born, right? From the day we were inside the womb of our mothers, little by little, we are our bodily entropy is increasing. Finally, it is falling apart, being part of the universe itself. That is why we are actually stardust. I will not explain further. In our bodies we have stardust. Ancient stars got destroyed, and those particles are have made this sun and our solar system. And this sun and solar system, and including us, we are also getting destroyed. Right? So universal concept, right? So that is why no matter how developed we are, we will never be able to stop people from dying or aging. But we can slow the process. That is what we are trying to make medicines. We are eating healthy stuff, exercising. We can stop aging, not slow the process. Or we can upload our mind to a computer or something, or artificial body, and then we can have our memory. Right? That's it. Our body we can't keep up. Right? So now see how far we can go with this concept. That is why I like it. I can explain many things, not just chemistry, right? One of the most profounding concepts of science, right? Okay, right. Understood. And the thing is, there's another part of reactions. Now we are back into entropy. Now we told about feasibility and spontaneous. And we under spontaneous and feasibility, we were talking about entropy, enthalpy, Then you must be asking me, what about rate of a reaction? Does it come under rate? Does it come under feasibility or thermodynamics? No, rate does not come under feasibility. Just because a reaction is happening faster, it doesn't mean reaction is spontaneous or reaction is feasible. You can't tell that. Rate is a different branch. It tells about something else. It has no connection with what? Feasibility or spontaneous. Remember, keep that in mind. Just because the reaction is happening faster, it doesn't mean reaction is feasible or not. Right? Feasibility has no connection. I'm telling you here because students are getting this wrong most of the time. That is why we are learning these two things separately. Under physical chemistry, but separately. But these two have a bit of a connection. I'll tell you later. Right? Feasibility and spontaneous or uh, thermodynamics. Right? Energetically favorableness has no connection. Right? It has no connection whatsoever. Put up across. Right? Why I am telling you this? I'll tell you this. Thing is, do you know diamonds and carbon? It's the same thing. Uh, Polymorph. These are polymorphs. The thing is, if you plot it in the graph, carbon is here, diamond is here, right? This carbon, this is diamond. Let's say this reaction is highly spontaneous, energetically favorable. Then why, if why in the on Earth, carbon is very graphite is found in abundance, right? You found it everywhere, but diamonds are very rare. Why? If it is the same thing, no, there's enough energy to do that. Highly spontaneous, energetically favorable, highly favorable reaction. No, even spontaneous temperature is enough. Highly spontaneous. If you calculate it, it is highly favorable. As per the calculation in the books, if you do the calculations, we shouldn't be able to even find a piece of graphite on Earth. All the graphite should have been converted into diamonds. But still, it has happened the other way around. Only very little amount of diamond is there. That is why it is rare. Even though it is spontaneous, highly favorable, it has not happened. Why? That also scientists were struggling to explain, and that is why, yes, it is highly favorable, highly spontaneous, but that reaction is happening very slowly. Why? The rate of this reaction is very less. The rate of the reaction and the thermodynamically favorable has no connection in each other. Very happening very slowly, right? So remember, thermodynamically favorableness, energy release, energy absorbed, endothermicness, exothermicness has no relation to how fast the reaction is happening. It will tell you reaction is happening, very favorable. But how fast it is happening is something else. Right? Why is that? Because activation energy is very large. There's a huge activation energy barrier. When you consider the reactant and the products, it is very favorable. But right in the middle, we have a highly high energy activation energy barrier. That energy barrier is so large, so therefore reaction is happening slowly. Right? To overcome this energy barrier, you need very harsh conditions, lot of energy, as you said, lot of huge temperatures, huge pressures. And that is why this takes millions and billions of years by nature to happen. Because in order to overcome this energy barrier, you need very special conditions. It takes millions and billions of years to happen naturally, but artificially, we make diamonds. Do you know that? There are some machines, US they have, there are some machines, those edges of these machines. For example, there are huge machines. These machines are designed to, they have blades. These blades are what? Cutting through the stones. For example, if you are digging a tunnel, these machines have blades. They can screw through these huge stones, right? To penetrate through these stones, you need a blade much stronger than the stone. So diamond is the strong, one of the strongest. So they need to make the tips of these blades with diamonds. So they have these machines. They have blades. The tips of these blades are made out of diamond, right? So these are artificial diamonds. No, not much different from the normal diamond, natural diamond. They what they do is they have machines. They put in carbon to these machines, and they are converting this carbon into diamonds. Then you must be asking, why can't we make jewelry like that? Why can't we be rich like that? Why? You can put it into a machine and convert it to diamonds. Why? Very good. It costs a lot of money. Especially the energy. It consumes a lot of energy. The energy bill costs more than the value of the diamond they are making. So it is not energetically favorable. Just because they need it only, they are making it. Otherwise, the current bill will go more than the price of the piece of diamond they are making. So that is why they don't, only on special occasion, not to make jewelry. To make jewelry, they don't do it. But then they want to make machines, blades. Then they do it because they have no other option, right? They have to make very sharp edges. To make those sharp edges, sharp tips, they are using this, right? Okay, so rate of the reaction and the feasibility or spontaneous or energetically favorable has nothing to do with each other, right? Okay, that is why we are learning about the rate of a reaction in a separate as a separate topic. And enthalpy, entropy, Gibbs free energy, chaos theory, randomness, all these things together under one topic. Okay, right. Two different branches. Right. Uh, Keep that in mind. Now we are moving on to calculus. These calculations are one of the easiest. Right. Now, put the topic calculating entropy changes. Are you still in India? Ah, here it is raining and you are in we are, I think, yeah. In Sri Lanka, most of the parts in Sri Lanka is under floods now. So yeah, now it's raining. That here it's kind of overcast, but we haven't got much raining. But for Colombo, so far we are safe. But everywhere except Colombo in our western province, it's flooded. So I think we are waiting for the rain to come because it's overcast actually. So at one point in future, I think in few hours time, we may get huge rain. So we are waiting for it. So yeah, we will get rain later. I guess. We had, huh? Really? Oh, oh my God. So is that the reason why you moved back? Huh? Okay, okay. Oh. Uh-uh. So where do you prefer the most? Gujarat or Chennai or Dubai? Yeah, all the vehicles. And what about Sri Lanka? Uh, Next time you spend like half. Really, you're a surfer? Oh, nice to hear. We have like I think east part of Sri Lanka. I think Arugambay and all. Yeah, it's very famous for surfing. And I think in some lakes also we have surfing. I heard like in Sri Lanka we have huge lakes, no? Man-made reservoirs. So in some of those, I think we have now even on them also we have tiny waves, even in lakes in Sri Lanka. Some lakes, right? Okay, good luck with that. So after the exams, you can have a good time here. Right. So calculating entropy change. So this is the only thing you need to do. Very easy calculations. Now remember, no, we have after this actually we are little by little moving on to another important thing called Gibbs free energy. Right. After that we are okay, and then we have again rate of a reaction feasibility. Yeah, with that we can move on to rate reaction rate. Remember, not that big actually. But kind of interesting, kind of like different than other topics. Kind of there's nothing much to remember actually. Calculations are very easy. Just to understand the initial concept. If you can get the concept at the beginning, it's kind of be walk in the park. So when it comes to entropy to work, just like enthalpy, even though we are talking about enthalpy, we are always talking about enthalpy difference, right? Delta H. So when it comes to entropy also, we cannot measure the entropy. We can only measure the entropy difference. Keep that in mind. We can only measure the difference in entropy. We can only measure the difference in entropy. Entropy difference, just like enthalpy. Enthalpy also we can't measure only enthalpy difference. Right? Entropy difference can be measured. Here also we can have S naught standard entropy likewise. The same as enthalpy. Right? The units of entropy is what? What do you think? The the unit of enthalpy is what? Moles per moles. Remember, enthalpy is joules per mole per Kelvin. Very good. Only this is that's the only difference. You just divide the enthalpy by temperature. Delta H divided by T actually, right? When you divide delta H by T, you are getting. Now remember, just like enthalpy, when it comes to entropy also, you must keep that this thing in mind. We were talking about something called, if you can remember, a system. What is a system? When we are learning about enthalpy, before that we were talking about what is a system and a surroundings. What's the system? What is there in a system? Closed or open? Okay, in a closed system, what is there in the what do you include in the system? Forget about samples, right? Now we have to move on to much more better explanation. When a reaction is happening, System means reactants and the products. That's all. Both reactants and products are system. Right? This is right. Huh? Everything that is in the equation. That's it. Reactants and the products. Nothing else. That's the system. Only the reactants. It could be even closed. So we are actually talking about closed systems. In a closed system or open system, system means this. Closed system and open system means interactions of energy. If the energy can what? Can be exchanged from the system to the surroundings. It is called open system, closed system, right? If the energy only the energy can be exchanged between the system and the surrounding, it is a closed system. Right? Here, energy can be exchanged. Now, if this is the system, what about outside? It is surroundings. What is meant by surroundings then? What's their surroundings? No, you got to give a very better meaning, a profound term. Surroundings. Everything except reactants and the products. That is the everything in the universe. Everything in the universe. In the universe, right? We are talking about the whole universe. Everything in the universe except reactants and the products. And reactants. Okay. Yes. Now, when you are doing endothermic or exothermic reactions, you are measuring the temperature of what? Surrounding or the system? Uh, no, you can't measure the surroundings, right? You measure the temperature of the surrounding all the time. You can only measure thermometer is there in the surroundings, even though it is a liquid. For example, this is the reaction mixture. Your thermometer is inside in the solution. Solution is actually the surrounding, right? You measure thermometer, temperature is measured in the surroundings, right? Is measured of surrounding. Keep that in mind. That is why in exothermic reaction, temperature of the surrounding goes up. Energy release to the surroundings. Endothermic reactions, temperature of the surrounding is going down. Decrease. You can only measure the temperature of the surroundings, right? Keep that in mind. Right. So now here this is a diagram of what? Closed system, right? Because reactants and products are there, it is not exchange between the surroundings. Now here we are talking about these entrophies in a closed system, right? Now can you define this? What is the name of this? Delta S naught means what? Now remember, now there are two different types of entropy. Delta S means entropy. This is delta S system, right? Delta S, very good. That's the thing. At standard temperature and pressure. Standard entropy. Uh, it's like a definition, but you just, it's about what? Bit means, right, more than definition, right? But the symbol, this symbol means, right, standard entropy difference, entropy change. I would say entropy change in a system. Right? Now they ask you must remember this equation in a system. Entropy within a system. We are talking about reactants and products only. Delta S system is equal to, right, sigma means total, right? Sigma delta S products, the reaction is happening, and what is the change of system entropy? Delta sigma delta S products minus, sigma means, right, total, sigma delta S reactants, right? We are talking about standard. Sigma means total, right? Sum. This means sum. Now I will give you a reaction using I will give you a question. You should find it right now. Find the entropy change of this system. I will give the reaction. If you can do this question, okay. Now you need to calculate the entropy change. Delta S naught system. You have to find. These are the data. Entropy into, this is the reaction. One of the easiest calculations. Here, focus on the states also. This is the reaction. You are given these values. Uh, S naught, magnesium solid, entropy is 32.60 joules per Kelvin per mole. H0, O2 gas, 205.0 joules per Kelvin per mole. S naught, magnesium oxide solid, it is 38.20 joules per Kelvin per moles. Applying the entropy equation, you must find this. Okay, very good. You have done it right. So it's basically you are plugging the values here. Magnesium oxide, it is what? 2 into 32.20 here. 200. Yeah, send me the word. And here 2 times of this, right? 32.60. And subtracting these values. Total of this minus this. So you must be getting minus 193.8 joules per Kelvin per mole. So that's all for today, right? Okay. Okay.